So this is another case study. This is a case study where we will simulate a gas turbine engine. So here's a schematic of our gas turbine engine. It's a very simple system that consists of a compressor pulling in ambient air at these conditions, and then that air is compressed. You can see the pressure ratio and the efficiency of the compressor, and fed to a combustor. And in the combustor, the air is mixed with a fuel, C4H10, and combusted. And you can see some performance parameters for the combustor. And the air-fuel ratio, or the percent excess air, is controlled so that the temperature of the combustion products coming out of the engine is 1200 degrees Celsius. And those products are then fed to a turbine that produces power. If we're going to simulate this system, it's always good to sort of plan ahead as to what our sort of strategy is here. So we need to determine the power provided and also the composition of the exhaust gas for this methane-fired gas turbine engine. So if I'm going to consider the composition, I need a fairly sophisticated combustor model that takes into account the chemical composition of the products. And I'll probably want to consider the products as a mixture as it goes through the turbine as well. So it's a little more difficult than maybe a more rudimentary thermal problem. So what are our input parameters here? We know the ambient air conditions, we know the mass flow rate of the air, and we know the compressor pressure ratio. And then we also know the performance parameters for these three components. So the compressor efficiency is 87%. The combustor pressure loss is 2%, and it's got a conductance, so conductance relative to heat loss of 5 watts per Kelvin. And then finally, the turbine efficiency is 85%. So I'm going to have to iterate on a couple things here as I go through this simulation. I'm going to have to iterate on the fuel mass flow rate in order to get the correct combustor exit flow. So basically, we're matching up the mass flow rate of the fuel required there. And then I'm also going to have to iterate on the excess air, the percent excess air, in order to get the right exit temperature. So those are two things that initially I'll set, and then I'll eventually adjust them in order to close up the equation set in order to get the correct combustor exit flow rate to satisfy continuity on the combustor, and the right exit temperature based on the chemical reaction. So let's go ahead and tackle this problem. So a couple things I know I'm going to want to do right away is I'm going to want to load the component library, because the component library is going to have my combustor model that I'm going to want to access. I'm going to want to set my units. So I like to work in SI units, and I'm going to use Celsius, kilopascal, mass, and kilojoules. And then I'm going to put at least one tab stop in here at 4 inches. And I'll go ahead and compile those equations, and you can watch it spin a little bit while it loads the component library up. So now I should have access to all of the models in the component library. And then I'm going to enter my operating conditions. So these include the ambient temperature, which is 25 C, the ambient pressure, which is 101.3 kilopascals. What else? I know the fuel is C4H10, so I can set that using a string. I know the pressure ratio of the compressor is 3.5. That's dimensionless. The mass flow rate of the air being sucked into the compressor is 0.1. And then I also know that the temperature coming out of the combustor has to be 1200 C. So I'll go ahead and solve that. Unit to right. I'm going to then set the performance parameters. So we said here that A to C is 87%, A to T is 85%, and the combustor pressure loss is 0.02 or 2%, and the combustor conductance is 0.005 This has to be in kilowatts per Kelvin to be consistent with my unit system. So let's make sure that solves as well. And it does. And then finally, I'm going to set the values of my iteration parameters. So these are the mass flow rate of the fuel, which if the air mass flow rate is 0.1, this has to be a lot less than that, so maybe 0.0005 kilograms per second. And then the excess air, which I'm going to set to be 20%. And again, we'll have to adjust that at some point. Alright, so now I'm just going to start working my way through the cycle. Starting with, let's do state 1. So state 1 is easy. At this point, my working fluid is pure air, so I can model it with air. So I'm going to set the temperature to be T ambient and the pressure to be P ambient. These are already in the units that I set for the unit system, so I can also get the enthalpy. This is the enthalpy of air. I'll just put air. At T equals T1, no need for pressure for enthalpy for an ideal gas. And then let's also get the entropy. S1 is equal to entropy of air. T equals T1, P equals P1. Alright, so we'll solve that. And we'll check out the arrays table. Maybe we'll put the units here just to make sure everything's right. So this would be in, let's see, kilojoules per kilogram Kelvin, I think. This would be in kilopascals. And this must be in kilojoules per kilogram. Alright, and yep, no unit problems, so that's all good. Then we will go through the compressor. So let's go ahead and set the exit pressure. So this is PRC times P1. I can get the enthalpy leaving a reversible compressor. That's the enthalpy of air at S equals S1 and P equals P2. And then I know the enthalpy of the air leaving the actual compressor will be greater than that. So this is going to be H1 plus, what would it be, HS2 minus H1 divided by eta C. Alright, and now I know P2 and H2. I can get T2 and S2. So T2 is the temperature of air at H equals H2, and S2 is the entropy of air at H equals H2 and P equals P2. And finally, you might as well get the compressor power. That is M dot, what did I call it? M dot A times H2 minus H1. So we should solve that. And check our units. So there's some unit issues. This has to be in kilowatts. And then maybe over here I have HS. Yeah, this has to be in kilojoules per kilogram. And hopefully that gets rid of all my unit problems, and it does. Alright, so the next thing we need to do is model the combustor. We've already loaded the component library, so we can now access those models. So let's go up here to function information. In the component library, we're looking at combustors, and there's 3 different combustors. The one I want is this last one, combustor 3, because this one actually will do the equilibrium chemical reactions calculations and tell you the concentration of the gas that's leaving the combustor. So it's a little bit more sophisticated than the other ones. So I can go ahead and paste that in here, and we'll go through and fix the inputs. So you can read about the combustor model if you'd like. I've read about it, so I kind of understand how it works here. So the first string is the fuel. I've already set that to methane, C4H10. The second one is the lower heating value, which you can provide to the model if you want. I'm not going to provide it. I'm just going to let it figure that out based on the fuel chemical formula. And then we have the inlet temperature and pressure. So the inlet temperature is T2, the inlet pressure is P2. And then we have a string that identifies the type of oxidizer, so it's either air or O2. We have air. And then here's the mass flow rate of the fuel, which is one of my iteration parameters. So eventually I will have to adjust the mass flow rate of the fuel so that the mass flow rate leaving the conductor, which is the combustor, which is one of the output parameters, is consistent with continuity. But for now, let's just put in my iteration parameter. I've already set the excess air to 20%. Eventually I will have to adjust this so that the temperature leaving the combustor is consistent with my required 1200 degrees Celsius, but for now we'll leave that. And then we have the pressure drop, which is 2%. We have the conductance, which I called UA, and it's going to give me a bunch of output parameters. The first one is what is the mass flow rate leaving the conductor, and then we have the temperature and the pressure leaving the conductor, which for us is T3 and P3. And we have the heat release, the heat loss, the efficiency, if I want that, the air-fuel ratio, the molecular weight, and then this last parameter is the mass fractions of the different constituent species. So there's 12 species that are modeled in the chemical reaction. This is going to give me the mass fraction of those 12 species. And I also would like to know what they are. So I'm going to add another output variable, which is an array of strings that tell me what each of these correspond to. And this should work now, so let's go ahead and save and solve. And yeah, we can go look at our well, first let's fix our units. So what's wrong here? This should be kilograms per kmol. This should be kilograms per second. And I think these heat transfers are in kilowatts. Yeah. So now we'll go to our array and we'll see that these are the different chemical species that were modeled. You know, CO2 and CO and so forth. And this is how much is in the combustion gas. Right. All right. So that seems to be working. Probably a good time now to do our iterations. So let's see, there's two iteration parameters that I've set up here. I need to get rid of these one at a time. The first one that I'm probably going to get rid of is m.fuel. So let's go ahead, and while I have a good set of guess values, I will hit the G button here to update all my guess values. And then I'll come down here and I will say that the equation that needs to be satisfied is that the mass flow rate leaving the conductor, so m.c out, had better be equal to m.fuel plus m.a. So then I'll go up here and I will comment out my assumed m.fuel, and then the last thing I'm going to do is set some limits for m.fuel, since I'm now going to be iterating on it. So up here I'll do a $var info m.fuel, and we'll let that go from a lower value, not of 0, that's probably a bad idea, but some very low number, and an upper value that's, I don't know, it can't be 10% of the airflow rate, would probably be way too high. So that's probably a good region to search in. And hopefully if I solve now, it will pretty quickly tell me the right mass flow rate of fuel is 5.46 kilograms per second, 5.46 grams per second. So that's my first iteration closed up. My second iteration is this excess air, which I need to adjust in order to get T3 to be equal to Tmax. I called this Tmax. So again, start by putting in the constraint T3 equals Tmax and comment this out. And then before I go ahead and solve, I'm going to come up here and add another $var info, and this one will have excess percent. Where lower is, I guess I want to search from 0 to upper is, I mean, this can be greater than 100% excess air, so let's go 400. Actually, maybe 500. I don't know. It doesn't matter, probably. And we'll solve. And it'll have to think a little bit now, but it comes to the solution that my excess air percentage needs to be 116.5, and that's now giving me, if I look at my raise table, the right temperature here at the outlet. And of course, before I do anything else, I want to update these gas values. And yeah, now I'm in a pretty good spot to move on and simulate the turbine. Okay, so simulating the turbine is actually a little tricky because we have not a pure substance going through it, but rather a mixture of gases. So we're going to have to make sure we're using the right properties for that mixture. But there are some routines in EES that provide properties for ideal gas mixtures, so we'll use those. So let's see, to find those you can either go to the substance information dialog or the function information dialog. Here I'm going to function information. More properties is what I want to click under thermophysical properties, and you can see there's 3 different choices here. Each of these gives you the properties of an ideal gas mixture. The top one gives you all the properties, and then the next 2 gives you either the thermodynamic properties or the transport properties, and we're only interested in the thermal properties, so I'll use the second one here, and we'll paste that into the equations window. And let's see, the way that this works is you give it the number of constituents, which for us is 12, to match the 12 constituents being given back by the combustor model. The chemical formula of each one, which we called $C, this array $C, so I'll just pass $C to this. The temperature, which coming out of the combustor is T3, and then the pressure is P3. The next item here is, because we're set up in mass units, will be the mass fractions. So this is X, and it's going to give me back the molecular weight, which I already know, so I don't want the enthalpy. The enthalpy, which is H3, H3, and then the entropy, which is S3, and the specific heat capacity, I don't think I want that either. So actually, let's set this to N and set N equals 12, like that. So hopefully now, when I solve, I get the properties at the inlet. Yeah, properties at the inlet to the turbine here. So now I got to simulate the turbine. Let's see, the exit of the turbine is P4, and that's just ambient pressure. And now I do have to iterate a little bit because I'm going to have to. I don't have an entropy function, right? So I'm going to have to guess a value of the temperature leaving my isentropic turbine, and vary that temperature until the entropy leaving the isentropic turbine is equal to the inlet entropy. So again, I have an iteration parameter, so probably I should label that as such, iteration parameter, and that iteration parameter is going to be, let's call it TS4. It can start out at whatever you want. You're going into 1200, so coming out at something like 900 seems reasonable. And now let's call the ideal gas mixture property again. So we're same concentration, right? We're going to give it TS4 here, and we'll give it P4, same concentrations, and then this is going to give me, I don't know, let's call this HS4 and SS4. So this is the properties leaving the reversible turbine. So this should now solve, and I can, I think, set my units, make sure that's all working correctly. So this should be kilojoules per kilogram Kelvin. Hopefully that fixes my unit error. And right now I see that, let's go back to my arrays table, SS4 is 8.758, whereas the entropy entering is 8.688. So I didn't quite get the right value of TS4, but I do have a pretty good solution, so I'm going to update my guess values. I'm going to get rid of this iteration parameter and require that SS4 is equal to S3. And that closes this up. And again, just because it's good practice, up here at the top I'll do $var info TS4, I think it's called TS4, and we will constrain TS4 to be between lower equals T ambient and upper equals T max. So just making sure it's searching for the right value of this iteration parameter in a range that makes sense. And hopefully if you solve, you won't have any troubles now. And it'll find that if my turbine was isentropic, I would be leaving at 837.5 degrees Celsius. So finally I can calculate the enthalpy. Oops, I didn't want to do that. The enthalpy leaving the actual turbine. So let's do that. So H4 is equal to H3 minus, what would this be? H3 minus H4 minus HS4. So that's the enthalpy change I'd get across the isentropic turbine, and then I got to multiply that by eta T, the efficiency of the turbine. And I can solve that, and that works okay. And finally then I can get the properties that are leaving the gas turbine engine. So to do that, I will call once again the ideal gas mixture props, and this time I'm going to give it, let's see, N, C, this is T4, this is actually an unknown, so we'll see if it'll solve for that. This is P4, and then here I have H4, which is a known, and S4. So I think this is probably an easy enough iteration that it could just find that, and it does. And I'll update my guess values, and it tells you that's what's leaving the what's leaving the turbine is going to be at, where's my temperature here, 893.1 degrees Celsius. If I want to know the turbine power, W dot T, that's M dot, in this case C out, because that's what's going through the turbine, times H3 minus H4. And if I want to know W dot net, that's just W dot T less whatever I need to run the compressor. And finally, if I want to know the efficiency, eta, this is going to be what? This would be W dot net divided by M dot fuel multiplied by the higher heating value of the fuel, which I get from the function higher heating value given the fuel. So that should give me the efficiency, I hope. And yeah, it does. Let's fix the units. This is 17.86. Maybe I also want that in percent. I must have some other unit problem here. This is going to be in kilowatts, and this is going to be also in kilowatts. Yeah, so that's good. The problem asked for what is the concentration coming out. I don't know specifically what somebody would be worried about coming out of a gas turbine engine, but let's figure out the parts per million of NO2, and that's just 1E6 times, let's see, actually NO2 is the 10th component here, so it's 1 times 10 to the 6 times x 10, and then the parts per million of carbon monoxide, maybe that's something to worry about, is 1 times 10 to the 6 times x, what is carbon monoxide? It's the second one, so x2. And if we solve, you can figure out that you have, where are we at here? Less than 1 part per million of CO, but 14 parts per million of NO2. And you can do things now like run a parametric table to look at how these different parameters are affected by your temperature or your pressure ratio or things like that. Maybe real quick, let's just run a quick parametric table where we change the temperature over some range of temperatures and look at how does that affect the efficiency and the net power as well as the concentration. So let's do a new parametric table, and we'll put in this table Tmax, and we'll also put in here the net power getting that you're getting, the concentration of these pollutants, and then the efficiency of the turbine. Yeah, okay. And we'll run this from something like, I don't know, 800 to 1400. And I have to comment this out to make this run. Come back to here and run the table. And you can see it cycle through. Once it gets the first one, it goes a little faster because it has pretty good gas values moving forward. You can see that as you increase the temperature, your parts per million of carbon monoxide goes up. The parts per million of NOx goes up a little bit. The efficiency doesn't change much. It goes up a little bit for this unrecuperated gas turbine engine, but the power goes up quite a lot. We could plot this if we wanted to, but I think that's good enough for this case study.